Today's daily good problem of the day is find the minimum area to cover all ones, part 2, number 3197. For this problem, we're given a 2D binary array called grid, and our goal is to find three non-overlapping rectangles that have non-zero areas with horizontal and vertical sides such that all the ones in the grids lie inside of these rectangles. All this basically means is we need to make three rectangles that hold all of the ones in the submatrix. And for example, we can't say, I guess this is one rectangle and this is one rectangle and then this is one rectangle. We have to have three rectangles with size at least one. Our rectangles are allowed to touch, so we aren't forced to do something like this. Something we can also note is no matter what, we will always get at least three ones in our grid, so we can always at least make three rectangles. So for this problem, I laid out, oh, my marker's big. I laid out some general steps that we're going to walk through. And first and foremost, I'll walk you through a mental model of the problem so we can kind of generally understand how these steps put together. So our goal is to cover every cell that contains a 1 using exactly 3 axis aligned rectangles. These rectangles can overlap zeros, but they cannot overlap each other. So we want to minimize the sum of the 3 rectangle areas. For example, we would not want to do one rectangle like this, one rectangle like this, one rectangle like this, because it does include a 0, which is allowed. We are not minimizing the area that we can consume. That's why this is the solution. We're minimizing the area we're consuming. Some key observations for this problem. For any fixed submatrix, the cheapest single rectangle that covers all the ones inside it is in a tight bounding box around those ones, meaning that tight bounding box would mean it's only touching ones. If there's no ones within a submatrix, for example, if we said this is a submatrix, there's no ones in it, the cost of this submatrix is 0, so it's not a valuable cost to us. So if we break our grid into 3 disjointed submatrices that together cover the whole grid, then the cost for our choice of cuts is the cost times the rectangle of A, which would be the area of the bounding box of ones within the submatrix A, and the cost of rectangle B and the cost of rectangle C, and we'll add these 3 together. All this means is when we split our rectangle or our submatrix into 3 rectangles, we will evaluate their costs. So 1 times 2 would be 2 for this one. 1 times 1 would be 1 for this one. 1 times 2 would be 2 for this one. And then we will add those up together to get our total value, which is the minimum that we will return. For this problem, if you look down at the topics, you could see that it is a enumeration problem. For this problem, enumeration will mean that we will identify the simple cut patterns and we will take the minimum total out of those identified patterns. So for this problem, we have 6 total patterns that are laid out right here. I'm not going to draw them, but we could take a look at them here from the editorial. We have 3 horizontal stripes, which would be here. We have 3 vertical stripes, which would be here. We have a top stripe with a bottom split, which would be here. We have a bottom stripe with a top split, which would be here. We have a left strip with a right side split, which would be here. And then a right strip with a left side split, which would be here. So these are the 6 total possible patterns that we're going to break our submatrix into. And within those, we will look for the smallest value. So for example, if we're looking at this problem here, one way we could split it is we could split it here. And then we would do something like this, right? So that way we have 3 total submatrices. So this is the top strip with the bottom split. Obviously, this is not efficient. However, this is how we would do it. We would evaluate their areas. So this would be an area of 3, area of 2. So we know how to do math. So it's area of 6. Then when we would move on to do something like our left split, we could do something like this where we have an area like this. Then the left side is split. We're going to notice that we can max or minimize the area here by splitting here. Splitting here. Then that leaves these 2 next to each other. So we'll dive into each of these patterns and how we're going to use them later on as well. Step 1, however, is we're going to identify a helper function that's going to compute the bounding box of an area, which is going to minimize the zeros within an area. We're going to try and squeeze out all the zeros so we can minimize that area. So let's go ahead and jump into this. So we're going to have a private function here. It's going to return an integer. We'll call it our area of bounding box. So this is going to receive 2D integer array called our grid. It's going to receive an integer, right 1, integer, right 2, integer, center 1, integer, center 2, and we will dive into those variables later. The main focus of doing this first is we're going to reuse this everywhere, and this is going to scan only the rows and columns inside of a submatrix that we pass it, and record a minimum row value, minimum column value, max row column. So we're going to look for cells that are only ones. If there are no ones seen, we'll return 0. This isolates the geometry from our enumeration code, which keeps the main loop easy to read, and it also allows us to kind of minimize the total area we use. So if you're interested in understanding this more, I'd probably watch yesterday's video where we find the minimum rows and columns and max rows and columns to find the minimum rectangle we can make instead of 3 rectangles in this problem. So moving on, we're going to treat empty or inverted ranges as a 0 cost. So if our right 1 is greater than our right 2, or our center 1 is less than our center or greater than our center 2, then we're going to return 0, because automatically we know that this value should not be greater than the second value. It's kind of like a left pointer and a right pointer. If it's greater than it, then our matrix kind of just doesn't exist. Moving on, we're going to initialize a couple of variables. M is going to be our grid length. Integer n is going to be our grid of 0 dot length. These are just to make our life a little bit easier. We're also going to have an integer called our top, which will be initiated to integer dot max value. That way, no matter what, everything will be less than it. And we're going to do the same for our left, bottom, and right value. So int left equal to integer value, right equal to integer dot max value, and integer bottom will be equal to integer dot max. Cool. Now we're going to clamp the grid bounds for safety. So this just basically means we're going to ensure that we don't go out of bounds. And we'll do this by updating our right 1 to be equal to the math.max of 0 and right 1. This is just so we don't go out of bounds. And then same thing for right 2 will be equal to math minimum of R2 and M minus 1. So we don't want it to go past M minus 1, and we don't want R1 to go below 0. C1 will be equal to the same thing, so math.max 0 and C1, and C2 will be equal to the map dot minimum of C2 or n minus 1. Cool. These variables are just meant to help us kind of easily get through this helper function. So this is, first we're making sure that our bounds are in order, so the left pointer is not in front of the right pointer. And then down here, we're making sure our pointers are still even in a valid range. That way we can go through this submatrix. Now this is the part where we actually traverse the submatrix. So we're going to have a double for loop. So for each integer I is equal to 0, as long as I is equal to R1, as long as I is less than or equal to the R2 value, then I can increment. Same thing for J, but with the C value. So for each integer J is equal to C1, as long as J is less than or equal to C2, J can increment. Cool. Now that we're within this for loop, it's the same exact thing as yesterday's problem. We're going to identify if it's a 1. So if grid of I of J is equal to 1, then we are going to kind of look at if the I is less than the current top value, then we're going to update it. Simply because we want to shrink that space as much as possible to keep the lack of zeros or the amount of zeros to a minimum, right? We're trying to squeeze as much room out of it as possible. So if our I is less than the current top value, top will now be equal to I. We're getting rid of any dead space. Same thing for the rest of the value. So if J is less than left, then our left value will now be equal to J. And if I is greater than bottom, well, now bottom is equal to I. And if J is greater than the right value, well, now right is equal to J. So what is this doing? Basically, we're going to, if the J value is greater than the right value, we are going to move that side of the rectangle to now be updated with a new right value. Because let's say we have a 1 here. Well, now our rectangle is going to have to compensate to hold that 1. I know, it's a great drawing. But hopefully you get the idea. We're compensating by addressing the new boundaries as we identify the extremes within our submatrix, because these values need to be in our rectangle. Now that we've passed this for loop, we have two options. Either we did not find a 1 in this region, meaning that the top, left, right, and bottom values did not change. Sorry, real quick, we need to update these to be the minimum values. Right and bottom need to be minimum values. But if they did not change, that means that we did not have any 1s in that submatrix. So if the top is still equal to the integer dot max value, we have to return 0. Because no matter what, the actual max value is 30, because the grid length can go up to 30. So if the top is still equal to integer dot max value, we have to return 0. Otherwise, we are going to update our height and width. So the height will be equal to bottom minus top plus 1 because it's 0 indexed. And width will be equal to right minus left plus 1 because it's 0 indexed. And then we will return the height times the width, because I know it's probably hard to remember doing all this. Our end goal is to find the minimum area, and the minimum area will be calculated by collapsing in the grid as much as possible by identifying the extremes of each variable. And by identifying the extremes of each variable within the submatrix, we can determine the maximum amount of elements that we can exclude from the initial grid that we passed in. Hopefully that makes sense. So yeah, this is our helper function. It's basically the exact same thing as what we did yesterday, except we're using it on a helper function. Now moving on to our actual function itself. Because of how we're handling the helper function, it's just looking at grids. It's not looking at shapes. It's not looking at sizes. It's shrinking, and that's it. Because of that, we can address each pattern separately without having to develop a unique way of searching it. We'll simply calculate it and pass it to our helper function. And that's exactly what we're going to do. So step 2, before we get into step 2, let's go ahead and initialize a couple variables. Integer best as of now will be equal to grid.length times our grid of 0.length. This is technically the save upper bound or the whole grid. I'm sure you probably know that. It's the whole grid. We're assuming that the minimum value right now is the whole grid, which is a fair assessment at the beginning. We'll also have an int m, which is equal to grid.length again, and an int n, which is equal to grid of 0.length. Make our lives a little bit easier. Now jumping into step 2, our first pattern we're going to address. So we're basically going to repeat this process for the next 5 steps. So we're just going to loop through and pass over the top, middle, bottom, and right values to our helper function, who will then identify the area of the passed over coordinates. So for each integer, we'll call this our I value is equal to, as long as I is equal to 0, as long as I is less than the m value, I can increment. Same thing for j. So for each integer j is equal to, so j is going to be equal to I plus 1. As long as j is less than our m value, j can increment. So the reason we're doing this is simply the way that we're going to be handling the bounds of our coordinate system. So let's go ahead and look at how we're going to do that. So int top, so the top bound will be equal to the, we're going to pass over to our area of bounding box. We're going to pass it our grid, of course, and then we could go ahead and scroll down here a little bit to see what we need to pass over. Grid, we're going to pass 0 as our first value. We're going to pass I as our second value. We're going to pass 0 as our third value, and we're going to pass n minus 1 as our fourth value. So this is kind of going to be a horizontal, strip. Let me kind of demonstrate. So as we go along, we are going to say, okay, so this is I, this is going to be I plus 1, right? So this is going to be the initial top row that we pass. That's why we call it top. And it's going to check that, and it's going to compare it against our best. Then it's going to do the same thing. So our I plus 1 is going to increment again, so I plus 1 here. And then we're going to check this. Okay, so this is a new kind of best because now we have 2 1s involved, but we also have to keep in mind that it has an area of 3. So we'll compare that against our best, and it will say, okay, even though it is technically better because it has 2 1s, it's not the best because our previous best had 2. So let's kind of finish this for loop so you can see the full pattern here. We're going to do the middle section. So this is going to be, again, area of bounding box, grid, and then we're going to pass I plus 1, and then we're going to pass j, and then we're going to pass 0, and then we're going to pass n minus 1. And the reason we're doing n minus 1 here is because that is the end of the end of the row. So this is the beginning of the row, this is the end of the row. This is the beginning of the column, this is the end of the column. So same thing for our bottom. So int bottom will be equal to area of bounding box, grid. We're going to pass our j value, n minus 1 value. We're going to pass 0. We're going to pass n minus 1. Then we're going to compute our total. So the int total will be equal to the top plus the middle plus the bottom. Basically, we are just passing all of the areas back, and then we're adding all those areas together. And then we'll see, okay, if the total we just computed is less than the best we've computed so far, then our best will now be equal to our total. Cool. So yeah, these are just going to be different coordinates passing in different columns. So we're going to compute those columns and see basically, okay, is this value better? So you can think about it like this. We're always going to be passing the full row because we're going from 0 to n minus 1, right? We're always going to be passing a row, but how many columns of that row? So we're going to do 2 columns of that row or 3 columns of that row, but we're always going to be passing a row. Now that that's done, we can move on to step 3, which is going to be our 3 vertical stripes. It's going to be the same exact thing, so I'll probably speed this up a little bit. We're doing the exact same thing, except we're going to flip the values that we pass. So let's go ahead and do that. Okay, now for step 4, we are going to do the horizontal strip, and then we're going to do 2 split boxes, right? So what we're going to do is we're going to pick a horizontal line I to form the top strip, and then we'll choose a vertical line J to split the bottom into a bottom left and a bottom right. We'll then compute the top cost once per I, and then since it doesn't depend on J, we'll just iterate the bottom split. Basically, we'll check, like, okay, is this the best split? Is this the best split? Other way around, you know. We'll just take it one at a time and see and identify the best split. So we can do for each integer I is equal to 0 as long as I is less than m, I can increment. And then this is where we're going to compute our top area. So int top area is going to be equal to the area of bounding box. We're going to pass the grid, of course, 0, I, 0, and n minus 1. Passing a whole top strip, we don't have to worry about limits or lengths. And then our for each integer j is equal to 0 as long as j is less than n, j can increment. And then we're going to do the same thing. So our int bottom left will be equal to an area of bounding. Then we're going to pass grid I plus 1. We're going to pass m minus 1, 0, and j. Then we're going to have our int bottom right, which will be equal to the area of bounding box, grid, I plus 1, m minus 1, minus 1, j plus 1, and n minus 1. So this is going to be looking at the left side of our bottom chunk. This is going to be looking at our right side of the bottom chunk. And basically, we're going to start off with a small left side, a large right side, and then we'll increment over to have a large left side and a small right side and identify which of those patterns is the best. And we'll do that by checking our total. So in total will be equal to the top area plus the bottom left plus the bottom right. That is not where that goes. And then again, if our total is less than our best, then best will be equal to total. Now, for the rest of this, we are going to be doing this exact same setup. However, we're going to just be kind of flipping it around. I am sure you could probably see there's actually a lot of similarities in all these patterns. So if you just take this and kind of flip this down here, boom, you got the same thing. Same thing here, right? So if you take this one and flip it here, then you could take it and flip it here, and then you can take this and flip it here. So something that you can do if feeling frisky and adventurous is instead of hard coding each scenario, you just you basically just have to code this scenario, and then you have to flip this scenario once, and you have to flip this scenario 4 times. I'm not going to cover that in this video, but that's how you would solve it quicker. I'm going to go ahead and hard code the rest of these. Actually, I already have it coded, so I'll just copy and paste it to make our lives a little bit easier. And you can look through as needed. And the best part of this is after we do all of those hard-coded solutions, all we have to do is return best. Because best will constantly be getting updated through all of these potential solutions. So if we run this, that passes our test cases, and if we submit it here, that is our solution. The runtime for the time complexity, I'm pretty sure it's m to the power of 3 times n plus n to the power of 3 times m plus n squared m squared. So it's a lot. But our space complexity is O of 1. So you know what? You win some, you lose some. But that's a pretty big win. So I hope you enjoyed this solution. Thank you, and follow for more daily code solutions.